Hello everyone, my name is Akir Ahmedin and this is my Physics 2212 Lab number 5 presentation. To introduce you to the lab, the description and purpose is to apply Faraday's law to explain phenomena of a magnet falling through an aluminum tube and compare predictions with real-world observations. Some fundamentals are Faraday's law, the Biot-Savart law, Newton's second law, as well as the third law, Ohm's law, the magnetic force on a loop, and the time derivative of magnetic flux of a dipole. And some of these formulas are listed to the right. And the major findings of this lab was that the experimental time was 1.24 seconds on average, but the computational time we expected was 0.642 seconds. So models and assumptions. The magnet was used to model a magnetic dipole, and the aluminum foil modeled a metal tube with mobile charges. And some assumptions were that gravity and the magnetic force caused by the aluminum tube are the only forces acting on the falling magnet, so we have negligible air resistance. So for the experiment, our system was the aluminum tube and magnet, and the surroundings were everything else, which wasn't anything in this experiment. So for the procedure, we marked the North Pole on the magnet, determined using the magnetometer on my phone. We dropped the magnet through the aluminum tube with the North Pole facing up. We recorded the time duration for the magnet to fall through the tube, and we repeated steps 2 and 3 5 more times and took an average. So some measurements and data. The length of the aluminum tube was 0.3 meters, the width was 0.008 meters, the inner radius was 0.024 meters, total radius was 0.032 meters, the mu, which was calculated from lab 3, was 2.11 amperes times meters squared, the magnet mass was 0.025 kilograms, and the average time was 1.24 seconds. So for some checkpoint questions, why can't we use a ferrous tube? Well, the ferrous tube is magnetic in its own respect, so the magnet would simply stick to the tube wall. What happens to the magnet? How does this compare to a magnet in free fall? The magnet experiences a magnetic force upwards that opposes the gravitational force, so the magnet takes longer to fall compared to if the aluminum tube was not there. So here's the glow script code that I have. So step 1, we set up the initial conditions, including the geometry of the tube and the moment of the bar magnet. In step 2, we calculated, which is the second block of code, we calculated the magnetic field using the magnetic field formula. The third block of code is calculating the change in flux using these several lines of code listed below. In this last part, the fourth block of code is using Faraday's law to calculate the current induced in each ring by the falling magnet. So these next blocks of code. So this top part is blocks 5 and 6. This uses the Biot-Savart law to calculate the force exerted on each current carrying ring by the falling magnet, and we're using Newton's third law to find the force exerted on the falling magnet by the whole tube of current carrying rings. The second to last block is calculating the net force, and the last block is Newton's second law to write the position, velocity, updating formulas. So here I have the graph and the model using the mu value from earlier, and we can see that the time deviated quite a bit from the actual observed model by almost a factor of 1/2. So lab questions. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring, which corresponds to clockwise and which corresponds to counterclockwise. Well, red corresponds to counterclockwise current and blue corresponds to clockwise, and this can be determined using Lenz's law. What happens to the dynamics of the system when you flip the magnet? Nothing would change regarding the speed of duration that it takes the magnet to fall down. However, the direction of the B field and the direction of the induced current would be flipped. How does the total time in tube of the real-world system compare to that of the computational? They were similar, but the computational model predicted a shorter time. It could be more accurate by modeling the tube as a greater number of rings. What does the shape of the velocity versus time graph tell about the forces? The shape indicates that the forces acting upon the bar magnet are changing with respect to time. Because gravity is constant, this illustrates the magnetic force as a non-constant force. So for the discussion, some model discrepancies. Cardboard and the aluminum foil may have increased the radius, but not contributed to the induced current. And some sources of error were human error when stopping the clock. Assuming air resistance is negligible, that might also been a source of error, and using an approximated mu value from lab 3. So what does it mean? So what if the resistivity of the conductor was reduced to 0? How would the dynamics of the magnet change? Well, the magnet would not fall as quickly due to Ohm's law. If R is decreased, then the current has to increase to maintain a constant voltage. What if holes or slots are cut into the tube? How would this affect the currents? So if we're lowering the area, then the strength is weakened. So you can think of this as a lowered end value. So the magnet would fall faster throughout the tube. It would be a more negligible contributor. So that's the end of my presentation, and I want to thank you for listening.